Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to answer the question that I know is just on everyone's mind these days, and that is, what is a conservative force? So let me chat about what we're looking at here. We're going to discuss young Timmy, who's going to start at this location here that I call position 1. And here's another picture of Timmy right here, and we're going to call this position 2. Now, we're going to discuss 3 different possible ways that Timmy can get from 1 to 2. And I'm going to call these different paths. Pathway number 1. Somehow Timmy goes down a ladder, maybe to here, and then walks over to here. Path number 2, we're going to imagine Timmy walking down this plank to this location. All right, we're going to take these one at a time, and what we're going to focus on is the work done by the gravitational force. Now, going back to path 1 here, so imagine Timmy's walking along this path to here, maybe walking down a ladder, then moving over to here. The gravitational force acting on Timmy is down, equal to mg. So we're talking about path 1. Oops. The work done here is going to have 2 terms. The work done for the first part of the path along here, work done for the second part of the path. The work done by the gravitational force for the first part of the path is going to be the force, mg, times whatever this distance is here. And I'm just going to call that h for height. And that work term is positive because the force is down and ultimately Timmy would be moving down. Now, as Timmy moves along this path here, I'll kind of simulate that. So as Timmy's kind of walking along, the gravitational force is still straight down. So gravity doesn't do any work along this path. So again, let me recap. So when Timmy goes from here to here, work done by gravity is positive mg times whatever that height is, and I'll label it in a moment. Work done from here to here is 0 because, at least the work done by the gravitational force, because the gravitational force makes a right angle to its velocity. So the work done by gravity along path 1, which is again this path right here, would be positive mgh plus 0. So the work done by gravity, the net work is mgh, and again where h is whatever this height is. All right, now we're going to discuss path 2. And path 2 is going to be this path along here. Now, as Timmy's walking along this path, and I'm just going to kind of freeze this right here, and draw in the gravitational force vector, which is straight down, equal to mg. Timmy's moving in this direction. So when we're calculating the work done by gravity, we want to take the component of gravity, I'll put mg, that's parallel to his motion, times whatever that length is here, and I'll just call this L right here. Because when you calculate work, you take the force in the direction of motion times the distance. Now, here is some sort of angle here that I'm going to call theta for a moment. And in this picture, if I draw myself a perpendicular, it's pretty easy to show, right, that this is actually theta as well. You know, run some numbers, like let's say this is 20 degrees. That makes this one 70, and this is a right angle, that makes that one 20. So when we calculate the work done by the gravitational force, it's going to equal mg times the sine of theta. This is the component of the gravitational force that's in the direction of motion. And then we would multiply by L. I'm not sure why I put 20 there. Let me go back. We'll just make that a generic theta here. So force times distance, L. Now, the sine of the angle theta, if we looked at this triangle right here, with this height being h right here, sine of theta would be h over L. So I'm going to go ahead and make that replacement. And when we take h over L and plug it here, basically the L's cancel and we get mgh. And again, positive, because the component of the gravitational force is down and right, and Timmy's moving down and right. And that's the sign convention for work terms. Now you'll notice that in both cases, we got the same value, positive mgh. Now, it turns out that it doesn't matter what the path is. Timmy could have done any path starting at 1 and ending at 2. And the value you'll get for the work term is going to be mgh. Timmy could have done this path, this path, this path. The path part isn't going to matter. And that's what a conservative force is, right? It's a force where the work done does not depend on path. The word not, very important, does not depend on path taken. Oops. Now, the gravitational force is typically the first force you learn about in a standard physics class. That is a conservative force. Other common ones, the spring force. So if I were to take a spring, which has some sort of natural length to it, and stretch it out, apply a force so that the spring stretches. It turns out the spring force is an example of a conservative force, but I'll save that for another video. If you take second semester physics, when you talk about what's called the Coulomb force, when you get charged particles together and they repel one another, that's called the Coulomb force. This force also is a conservative force. Anyway, I'm going to keep this to just physics, first semester physics topics. So now, why is this so important here? Why do we care? Well, because when a force is a conservative force, it's going to allow us to do kind of a cool thing. Because we know that as long as Timmy starts here, in fact, if Timmy starts anywhere at this height, and then Timmy ends up anywhere at this height, then we'll know that the work done by gravity is going to be this mgh term. And what we're going to do is we're going to define a new thing called a potential energy. So here's how potential energy is defined, or maybe I should say the difference in potential energy is defined. The difference in potential energy for a system is equal to the opposite of the work done by the force. So in this case, our PE2 minus PE1, which is standing for potential energy 2 minus potential energy 1, would equal minus mgh. Now, potential energies are terms that are arbitrary in that you can measure them for wherever you want. Where you decide to call your potential energy 0 is called your datum. In this problem, if I just did this and we put a datum right there, what that would do in my math here is force the potential energy 2 to be 0. And you'll see that basically we'll have minus PE1 equals mgh. This term, mgh, is what's referred to as the gravitational potential energy. It's basically what it is it's the work that gravity will do on an object as it goes from some location to your defined datum. So, next question is, where are we going to use this? Well, what we're going to do, and I think I'm going to need a little bit more room here, so I'm going to actually save this picture. So let's say we have some sort of system. Doesn't matter what it is, and at what I'm going to call state 1. the standard theorem of work and energy says this, that the kinetic energy of that system, which I'm going to call KE1, plus any work done on that system from state 1 to state 2 is equal to your new kinetic energy, KE2. Oops. What we're going to do now is add potential energy terms for conservative forces. So I'm just going to add a PE1 and a PE2, and I'm going to take this and just move this over. I think that's what I meant to do. So the idea is, for conservative forces, we can define these quantities called potential energies. Then the sum of your potential energy plus your kinetic energy represents the total energy of a system. Now, if you've already seen my videos on kinetic energy, you know that kinetic energy is energy due to motion, so it's speed dependent. Potential energy is defined as energy due to position. I can write that a little better. Again, let's talk about a gravity problem. Here is some sort of object. It has a certain mass. Then it's got a gravitational force acting down equal to mg. And it's a certain height here from what I'm going to call my datum. So what we call the gravitational potential energy for this would be mgh. And if you think about, well, what does this mean? It's the work that gravity will do on this object as it moves from this location to anywhere at the datum. And again, you'll notice it's position dependent. It's got a height in it. The higher this object is, the larger its potential energy is. The lower the object this is, the lower its potential energy is. So I think that's good enough for this video. I think I'll just kind of recap this and then end it. So conservative force is a force where the work is not path dependent. When you have conservative forces, you can define what are called potential energies for them. And here's how where they come from. The difference in potential energy for any conservative force is equal to the opposite of the work done by that force. This is basically how the potential energy terms come about. And then potential energy terms can be added to our work energy theorem to give us what I would just call a more generalized work energy theorem, taking into account the energy of a system due to its motion and the energy of a system due to orientation and position. Now, gravitational potential energies are not the only types of potential energies. Again, springs can carry a potential energy. There's what's called electrostatic potential energy. So anyway, just meant to be an introductory video about the conservative forces and potential energy terms. I hope that this has helped you out. Have a great day.